my name is Lindsay Mitchell. I'm going to be talking to you about the physics of the piano today, which was my favorite, most interesting extra credit lecture. So first I'm going to talk to you a little bit about the two main different kinds of pianos. We have the modern Steinway, which has steel strings, hammers covered with felt, 88 notes, and a huge, monstrous range of notes that you can possibly have compared to the Cristofori piano, which has about 1/4 the amount of frequency coverage. There are also half as many notes, roughly, and the hammers are covered with parchment, and the strings are made of brass instead of steel. So the shape of the piano, it's made to basically create waves on a string. There's the Pythagorean scaling, which basically states that the doubling the length of the string reduces the frequency by an octave, so the longer the string, the lower the note. However, this isn't very practical for a modern piano, and to avoid this problem, we started increasing the mass per unit length, which is used by wound strings. Wound strings basically means like a steel core with copper winding around it. So we need these wound strings. However, instead of just using thicker strings, we need them to be wound because you need to maintain the string stiffness for an idea of a string standing wave frequency. They're perfectly harmonic, and so that's why we have these equations here, which cover the basically harmonic tones of the frequencies. And winding adds very little stiffness compared to the actual core. So effects and stiffness is called enharmonic distractions or whatever, deviations. So these deviations aren't large, but we can really perceive them. A way to kind of count that is through cents, which are basically changes in the octave notes from the pure octave. So there are 100 cents in between each note. And for notes spaced by an octave, they need at least 100 cents or somewhere around that, like 98 to 102 to sound quote-unquote good. The rails-back stretch basically is the amount of an octave stretching that varies across a keyboard. The stretching is the largest in the bass area, which is down here. You see it's a longer gap, and this is in cents compared to the note. And you can see the middle C is where it's almost on top of the actual pitch, and then here is where we're getting higher, and it is a bigger deviation than the center, but not quite as large as in the bass. So hammers. In the modern hammers, they are wood core covered with a dense felt. The hammer is attached to an escapement mechanism, and the speed of the hammer depends on the key press. The hammers are largest in the bass, about 10 grams, and smallest in the treble, which is the higher notes, which are close to about 3 grams. So then there was a really different kind of concept of how a hammer should be modeled. The first idea was with Hooke's law, which is basically modeling the hammer as a spring, and the relation between F is equal to negative kz. But the more effective kind of model was found to be F hammer is equal to negative kz cubed. Another thing that had to be considered when kind of finding out the physics behind piano was where the hammer should strike the string. So for a hammer to strike the string in the correct area to make what we consider the note. The hammer-string interaction is quite complex, and it was found out that the hammer should strike the string at a nodal point roughly 1/8 of the length from the end. So this means that the 8th partial is suppressed. And if you look here, I have a small little graph. This is where you have all of them are represented, and then you have 3 nodals, and then here's 4. So this is the third kind of loop or whatever. So that's what we're talking about when we say partials. But when you have that strike, there is a perception of a missing fundamental, which is where it's hit on the node. So that sound goes away, and it's actually amazing. But most people can actually hear that. Oopsie, sorry. The last thing we have is about the soundboard, which is a thin piece of spruce, which is generated, which is then motion is generated on the soundboard, and that's how we perceive the actual sound. It has like breathing models because the soundboard is almost like kind of like a diaphragm in your body that's expanding and contracting. And we have a few of like the differentials and the math behind what we hear. So this is basically the overall gist of what happened in the lecture. We talked a lot about the different physics behind all these different parts of the piano. So thanks for listening.